The question is, the transfer function of a discrete LTI system is given by h of z equal to 2 minus 3 by 4 z inverse by 1 minus 3 by 4 z inverse plus 1 by 8 z power minus 2. Consider the following statements. S1. The system is stable and causal for ROC mod z greater than half. S2. The system is stable but not causal for ROC mod z less than 1 by 4. S3. The system is neither stable nor causal for ROC 1 by 4 less than mod z less than 1 by 2. Which one of the following statements is valid? First option, both S1 and S2 are true. Second option, both S2 and S3 are true. Third option, both S1 and S3 are true. Fourth option, S1, S2 and S3 are all true. Now we will see the solution to this question. Given h of z equal to 2 minus 3 by 4 z inverse by 1 minus 3 by 4 z inverse plus 1 by 8 z power minus 2. Now we need to factorize the denominator. That is, we need to find the factors in terms of the z inverse. Clearly by inspection we can see that the factors are 1 minus 1 by 2 z inverse and 1 minus 1 by 4 z inverse. So we can write h of z as 1 minus half z inverse plus 1 minus 1 by 4 z inverse, because 2 minus 3 by 4 z inverse can be splitted in terms of 1 minus 1 by 2 z inverse plus 1 minus 1 by 4 z inverse. So separating the both terms now, we can get it as 1 by 1 minus 1 by 4 z inverse plus 1 by 1 minus 1 by 2 z inverse. This is the given function h of z. Now in the statement S1, the ROC given is mod z greater than half. Now for S1, mod z is greater than half. Now we need to find whether the system is stable or not, or whether it is causal or not for this ROC given, which is mod z greater than half. Now whenever mod z is greater than A, we know that the inverse transform of 1 by 1 minus A z inverse as A power n into U of n. And whenever mod z is less than A, we know that the inverse z transform of 1 minus A z inverse as minus A power n U of minus n minus 1. Using these two equations, we can get h of n for the ROC given. Since mod z is greater than half, 1 by 4 whole power n U of n plus 1 by 2 whole power n U of n. This is the value of h of n, which is the inverse z transform of h of z for the given ROC. Now we can simply see that mod z is greater than half and the poles are nothing but 1 by 2 and 1 by 4. Since mod z is greater than half, in which the ROC is right of the rightmost pole, we can say that the system is causal. Also, the ROC mod z greater than half includes unit circle, so we can say that the system is stable for the given ROC. So, the system is both causal and stable for mod z greater than half. So, we can simply see that the statement S1 is true. Now, we will see the system for mod z less than 1 by 4. Whenever mod z is less than 1 by 4, this term as well as this term results from this equation. So we can write h of n as minus of 1 by 4 whole power n U of minus n minus 1 minus of 1 by 2 whole power n U of minus of n minus 1. From this we can see that since mod z is less than 1 by 4, these two signals are left-sided signals. So the ROC is not to the right of the rightmost pole, so it is simply not causal. Also, the ROC mod z less than 1 by 4 does not include mod z equal to 1. So the system is not stable for the given ROC. But in the statement S2, it is given that the system is stable but not causal. So the statement S2 is false. Now we will see the ROC 1 by 4 less than mod z less than 1 by 2. For this ROC, we get h of n as minus of 1 by 4 whole power n U of minus n minus 1 plus 1 by 2 whole power n U of n. Since ROC is not to the right of the rightmost pole, we can say that the system is not causal. Also, the system does not include the ROC mod z equal to 1. So, the system is not stable. In the statement S3, it is given that the system is neither stable nor causal. So, the statement S3 is a right statement. So we can see that the statement S1 is true, S2 is false and S3 is true. So we can conclude that both S1 and S3 are true. So the right option is option C.